Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'd like to talk about the Jim Gray eScience Award. It's hard for anyone to work for very long in the field of eScience without knowing about Jim Gray. Jim truly was a leader in every sense of the word. He was at the forefront of the field and of the area that we focus our energy on. And it was because of that leadership we established a leadership award at Microsoft, which we call simply the Jim Gray eScience Award. So we established in this the year after. Jim Gray disappeared in the year 2007. We established this in 2008 as a special tribute to Jim. And we've had 7 wonderful leadership type individuals who have received the award over the last 7 years. And here you see them all displayed. We have one of those with us. Anthony Williams is here. And his name is spelled wrong on the slide. It's Anthony, and I call him Tony. He's sitting here in the back. You'll hear him tomorrow in one of the sessions and learn more about it. So it's my great pleasure today to announce the 8th winner of the award. Oh, look, with a lot of applause here. We come to Paul Watson. It's always appropriate, despite the fact that probably most of you already know Paul, to say a few words about him. And these words here are displayed on this slide. It says a little bit about his background. It's very hard to capture one's background in a simple slide. So in a few minutes, what we've asked him to do is actually talk about a very important topic, which is cloud computing in eScience. And so that really, I think you'll learn more about him through his talking than through all the words that we can say. But for the moment, it would be great, Paul, if you would come up here. We'd like to honor you. So with that, let's welcome Paul.
Okay, well, thanks to Harold for those kind words. It's a real honor and a pleasure to be here to talk to you today. I wanted to, as Harold said, to talk about some of our work on cloud computing. And we've worked with clouds across a wide range of eScience projects, but I thought I might focus on one particular project because it's a little different perhaps to typical eScience projects, the one that I spent most time in the last 3 or 4 years. And this is a project about social exclusion. So social exclusion is one of the great problems facing society today, and we've been looking at how we might address this using eScience techniques. And in our project, we have a wide range of different disciplines, including sociologists. And if you talk to a friendly sociologist and ask them for a definition of social exclusion, then they will come up with something like this about the fact it's the result of related factors that prevent individuals or groups from participating fully in the economic, social, and political life of society. And that seems like a really a theoretical definition, but actually it affects a lot of people. So in my own country, in the UK, there's about 1 in 6 people who are affected by social exclusion. And this is because it includes older people with a range of medical problems and perhaps suffering from isolation. It includes people with disabilities. and it also includes increasingly young people on the margins of society. And if you talk to experts in this field about what the effect of digital technologies have been on social exclusion, then they're very clear, and they'll say that, well, digital technologies have had a real effect on social exclusion, and that effect has been to make things worse. And I was surprised when I learned that, but then you look through the evidence, and it's actually hard to get a job these days if you can't use computers, and that might be because you don't have access to them, it might be because you've never developed the skills to use them, or it might be because you have some disability which actually prevents you from using computers. And then there's the fact that in order to save money, increasingly governments are moving services that they're aiming at people who are socially excluded, they're moving them online. And so that actually makes things difficult for the large proportion of people who are socially excluded who lack the ability to get online and access those services. That's a sort of catch-22 problem. So there's all of these issues which mean that people who are socially excluded aren't reaping the benefits that most of us are from the march on of digital technologies. And the evidence is that things are getting worse. And so this is a rather dystopian, perhaps depressing view of the future, that over time people like ourselves will pull away from people who find themselves in this unfortunate position. And so a few years ago, a group of us decided to pull together a project and have a look at perhaps different novel ways in which digital technologies could help people who found themselves in this position. And so this is the project that Harold mentioned on the slide. So this is the side project, Social Inclusion Through the Digital Economy, which is the one I'm going to talk to you a little bit about this morning. And the aim of that is to explore this question of how can digital technologies transform the lives of excluded people and communities. And it's a project that we do at Newcastle in collaboration with Dundee University in Scotland. And it's a very wide-ranging project, so it's about $20 million, so roughly at any time we've got about 30 or 40 people working on it across a wide range of disciplines and sub-projects. And this just gives you a flavour of, even this is only a small part of it, but for example, if you look at the top left, that's some work that's been done in the project trying to address the problems of people with dementia. So dementia is a growing problem in society. One of the problems with dementia is people lose their ability to remember how to conduct a series of tasks. So what they do is they set off to try and do something, they get halfway through it, and then they can't remember what the next step is. And so this is work that we've been doing to see whether in the kitchen, whether you could have sensors, so sensors around in the utensils and the cupboards and so on, which were working out what people were doing, and then when somebody got stuck, so they got to the point where they couldn't remember what to do next, then could the system prompt them either audibly or visually to help them to carry on and complete the task they'd started. The bottom left about mobility, so this is if you ask older people about their main concern, they'll tell you that it's mobility. So the ability to get around means that you can go and socialize, it means you can go shopping, it means you can see your friends and family. If you can't do that because you lose your mobility, then your quality of life rapidly diminishes. And this is a particular problem for people who live in urban areas who rely on the ability to drive a car. And there's a lot of evidence that as people get older, they start to drive a bit more after they've retired because they've got more time, and then suddenly there's a cut-off, and nobody's really sure why that is. You can interview people and you get a whole series of results back. So we've got some work in the project with transport researchers where we bought a car, we instrumented it, so every time anybody turns the wheel or presses a pedal, we capture that information, we capture where they are on the road, and we also instrument the driver. So we fit them up with a bio belt, which allows you to measure their heart rate, which is a good proxy for anxiety, and then we drive them around in particular situations and we capture all of this information in order to try and understand why this is. And although the work's still ongoing, one of the things that we've discovered, for example, is that so if you're in a country that drives on the right-hand side of the road, then turning left against oncoming traffic is a real problem for older drivers. And one of the reasons seems to be that as you get older, you lose your ability to judge speed and distance, and so it's harder to work out whether you can fit through a gap in the traffic that's coming towards you. So this project's starting to get these sorts of insights, and the idea is, armed with that, you can then influence policymakers who design road layouts and people who design cars in order to try to make them better for people who are older and suffering from some of these sorts of problems. The top left, so we do work with musicians, and so this is trying to find ways to motivate younger people to learn some digital skills. So this is getting them to do some music making. Kids tend to be interested in music, so they make some music, they capture it, and then they're taught to use software to manipulate that music, create new music from the original sounds that they made. And so in this way, what you're doing is you teach them these transferable skills they can apply in other areas, which hopefully help them to get jobs, but you're doing it in a way where they're self-motivated. You don't have to force them to do this because they're so interested in music and what you can do with the software that's provided. And then the bottom one, we do a lot of work with people with Parkinson's disease. I'll come back to that in a while. And one of the problems with Parkinson's disease is tremor. So people suffer from shaking. And the question is, well, what can you do about that? So doctors will give patients drugs, but the problem is that how do you know whether those drugs are effective? How often should they take the drugs? What strength should they be? So this is an experiment with a sensor which measures tremor in a discrete way, and then this is actually with a head-up display. So this is Google Glass, but you can do it through a mobile phone as well, which then gives a prompt to the person suffering from Parkinson's disease to tell them that they should take a pill at a particular time. And of course, what this means is that they're not just taking pills at regular times that are preset, they're taking them when they really need them. And of course, the system takes into account the strength of the medication that they've taken on, so it makes sure they don't take too much of the medication. So this is 4 examples across a huge range that we work on in the project. I thought I'd focus on 2 just to see some of the work that we do with cloud computing and data analytics. So this is one on a problem that a lot of medics have. So if you talk to medics, then one of the things that they'll say is that if they could understand more about people's lives, then they could provide much more effective treatment for them because they could personalize that treatment. And there's a lot of problems that people have, particularly older people, with diseases like diabetes, obesity, cardiovascular disease, where the effect of the disease can be mitigated if you can know something about their activity levels in their daily lives. But the problem is that at the moment what happens is that the medic gets somebody into their office and they can ask them questions. They can say to them, how often do you exercise? How intense is your exercise? But of course, as anybody who's gone to and talked to a medic, in some cases we're prone to exaggerate what we tell medics about how much exercise that we actually take. And even if we try to be accurate, it's very difficult to get an ideal picture of how much exercise we have and whether it's intense exercise or just light exercise. So the question was, could we try and shine a torch into people's lives so that medics would know much more about how much exercise they were taking so that they could personalize the treatment for them. And so we've been doing some work with sensors on this, and you can see here we're doing some trials in a local hospital in Newcastle. This is a patient being with a sensor in the form of, it looks like a watch, being strapped onto their arm by a nurse. And I'll show you a little video of this in action so you can get some of the idea of the information that you can get from it. I'll explain a little bit of the background to the video, which is that when I realized I wanted to do a video, then I talked to my research group, who are mainly in their 20s and their 30s, and I asked them, well, if we're doing a video, we need a model, so we need somebody who's getting on a bit, might need some help before too long, and can you think of anybody we could use as a model in the video? And so one name kept coming back again and again, and so you'll see this when the video starts. So this is the accelerometer. It's a triaxial accelerometer, measures in 3 different axes, acceleration, strapped on the wrist, and here's the model coming down the stairs at our university, and then going into one of our labs, into Culture Lab. And if we run this again, it's a bit faint actually, but underneath you can just about make out the signals from the accelerometer. And if you can see the green signal, which is the one at the bottom, you'll see peaks, which is as I walk down the stairs, you can see every step, because the green is down my hand as I walk, so it's measuring the swinging arm. But you might also be able to see that the amplitude of the peaks changes as I walk down the steps. So down the steps, the amplitude is greater than when I'm walking on the flat. And so by doing analytics, so we've got people who can do lots of signal processing, then we can tell the difference between walking on the flat, walking upstairs, walking downstairs, as well as whether people are sitting, walking, running, and various other sorts of activities in between. So what we want to do is capture this data, and we've been doing this over the last few years, and then analyze it using a series of techniques to try and provide a profile of people's activity. It's also interesting the other things that you can get out of this information. So here's another little video. So this is if my wife were here, she would say this is me doing something I'm good at. So I'm sitting down, drinking tea and reading a newspaper. And when we go to split screen in a second, then, so it looks like you can't imagine any useful information, but if you can see it, then when I grip the cup, then there's a real spike in the accelerometer. And then as I lift the cup to my lips, you get a measure. There's a little bit of shake there, not too much, but a little bit. So medics find this sort of information useful because as you get older, one of the problems that stops you from living a healthy and happy life is if you can't manipulate objects anymore. So the ability to grip is really important, and it means that you can cook and clean and generally look after yourself. So medics are interested in how people's ability to grip changes over time. And then, of course, back to the work I told you about earlier about Parkinson's disease, anything which allows us to measure tremor and to analyze that, again, gives us this ability to personalize the treatment that we can make for people. So that's one project. I've got another one later. But, of course, what we need to do is to be able to extract that information that's hidden in the data from these sensors. And given the title of the talk and what Harold said, you won't be surprised to learn how we want to go about, how we've been trying to store, share, and analyze data over the past few years. And so we've been using cloud computing ever since it first came along. I think that's a Microsoft cloud facility somewhere in the Pacific Northwest. And I believe there's about 200,000 computers in that one facility, which is about, I'm told, 6 football fields in size. I think I got this from Dennis Gannon, so I think that means 6 American football fields, but they aren't very different, I believe, from the more standard international soccer fields. And so you've got 100,000 machines in one facility, or 200,000 in this case. And what you can do is you can go and grab them. So you go over the internet, and you can grab these machines, processors and storage as and when you need it for your research. And you pay as you go. So the nice thing about this is I think not so much the technology, but the business model. So the fact that you only pay for those resources that you use when you use them. And we found this is a really good fit to the sort of research that we do, and the research that goes on more widely in eScience. And there's 2 sorts of standard reasons for this. So this one is where you have growth in access to data or a service. If we go back a few years to the grid computing days, there was a lot of emphasis then on people making available analytic routines as a service, and they would quite often put them on their laptop or their desktop. They would go to a conference, present a paper on it, they would get people excited by it, and then they would say, and here's the end point of this service. And people would go to that end point and try to use it, and the system would just collapse. So because it was on somebody's laptop or desktop, and it had no way to scale up as the number of users or the amount of data that it was processing increased. But with cloud, you have this potential. As you increase the number of users, you can grab more resources and cope with that additional load. And then the other one, which I think is not just to match the way we analyze data in universities and research labs, but also matches the way in which we think about science, is the bursting pattern. So what happens is that we get a dump of some data, we want to analyze it so we can grab the resources that are needed to do the analysis, potentially hundreds or thousands of machines, do the analysis, and then stop paying for those machines while we look at the results, perhaps write a paper about it. And then other examples might be an event. So let's say we have some sensors that are, say, measuring river levels in a floodplain. What we might want to do is when the levels get above a particular height, then we may want to trigger a model which is going to predict the effect of the rising river levels over an area and the effect on people and buildings. And so we can do that. Again, when the event happens, we can grab the resources we need in order to run the models. When we finish doing that, and this might only happen every few months or every few years, then we don't have to pay for the resources that we need. Same with new algorithms. So somebody cycling into work on a morning has a bright idea for a new sort of algorithm. They can come into work, grab the resources they need in order to analyze the data sets that are available to them in the cloud and see whether their algorithm really is better than previous algorithms. And so this agility, this ability to grab resources when we need it, I think this really has a transformational effect on the way in which we do science. But the question is, can scientists actually realize this potential that clouds offer? And I think this is a real problem. So our own work has been with probably about 20 different scientific groups and also some science companies. And one of the things that we find is that there's a small group of scientists with resources and skills who are really able to do the analytics, build scalable systems so that as the amount of data they have to deal with increases, then the computation can also scale out. But these skills are very few and far between. Not many groups do actually have these sorts of this sort of ability. And the sad thing is that there's this long tail of scientists who are the people who could really do with the access to resources which clouds potentially gives them, because they don't need their own large servers, they don't need access to national facilities. They could just go out and grab the resources that they need. But they're the people who don't have the IT skills to take advantage of those resources. So again, this is another sort of catch-22, that the people who could benefit most from clouds are the people who can't benefit from clouds because they don't have the IT skills to do so. So people here, for example, you're all in the head of this curve, but there's a lot of people who would never go anywhere near an eScience conference who could really benefit from the sorts of techniques, tools and techniques that you're developing, who just don't have the skills or the resources to do so. And the reason for that is, I think that it's just plain hard. So I'm a computer scientist, I work in a computer science department. We take in, into our research group, people who've got, say, masters, occasionally undergraduates in computing, and really even people with a master's degree in computing who've done an undergraduate program and then an advanced program in building scalable systems. They're only just at the stage where they find they're able to build out these sorts of scalable systems. There's just so much you need to know and so much experience that you need if you're to really provide efficiency in the systems that you build. And the reason is that if you look at what we need in eScience, it's quite demanding. So we need scalability. So all the examples I showed on the previous slide of the potential for clouds rely on somebody who's able to build scalable systems. So as the amount of data increases, the resources that you give this system increase in proportion to that. Or that can scale out as the amount of computation that you're trying to do gets beyond the point where you can do it on a single node. And then security. So for healthcare applications, such as the ones that we deal with in the SIDE project, and other applications where you're dealing with, say, confidential data or data where there's some IP involved in it, then you need to build systems that are secure. You need to have control over exactly who's allowed to see and do what with the data in the system. And then you need to build systems that are reliable. And so you need reliability because, for example, if you go back to the sensor example, what you want to have is the patient comes back into the clinic after a week of wearing the watch. They're about to see a doctor, say 10 minutes later, and in that 10 minutes you need to extract the data from the watch, analyze it, and produce a report for the medic so that they can then personalize the treatment for that patient. And if the system fails in that 10 minutes, it's down, it's not able to do the analysis, then you've lost that ability for the medic to really personalize their treatment. So trying to find people who can build systems that are scalable, secure, and reliable is actually, I think, very, very challenging. And when you go to a cloud, you're building from quite a low base. You can grab basic compute power, you can grab storage, but it's up to you to build these complex systems above that. And so we think this is one of the reasons why, although clouds have this potential to really transform a lot of science, their effect's been really limited. It's due to the problem of lack of skills. So what we did a few years ago was to think about a different approach, and that's really this one here. So rather than have everybody build from the ground up a system, an application for their particular project to do whatever they were, to deal with whatever data they wanted to deal with, to do whatever computation they wanted to deal with, is it possible to think about some middleware? So it's some middleware which does 80% of what people need to do in these applications, so that the amount they have to write is much more limited, and the complexity of what they have to write, the software that they create, can be more focused on their application rather than generic things about how do you scale up computations across the cloud, how do you build reliable systems, how do you build security into your systems. And so about 9 years ago, pre-cloud, we were in the middle of the grid computing era, we decided to try and build out a system to do this. And so we took best of breed components that we could find from around the grid eScience world. So we took the best distributed file system we could find, we took the best metadata store, we took the best workflow engine and so on, and we integrated these together, and this was to be our platform. And the idea was that we would run this on our own servers, and therefore users could just go online and use the capability which we'd provided by already integrating these systems together. And I have to say that it was a complete failure. It's one of the biggest disasters that we've had over the last 10, 15 years. And there were a number of reasons for this. One was that all of these different systems were almost completely incompatible in some important way. So, for example, almost all of them had their own security model, and the security models just couldn't be made to fit together. And then there was the problem of scalability. Most of them weren't actually particularly scalable. For example, finding scalable workflow engines at that time was very difficult. So as you increase the amount of work that you wanted to push through the workflow engine, it couldn't increase its performance. And the final problem, which wasn't one that we expected, but we'd started to work with some small companies, some startups and some SMEs who had some science-based product or service that they wanted to get out there to customers. And it's surprising in industry, and we found later in a number of research groups, that you're not allowed to deploy software on your desktop. So almost all of these components that we were integrating together had some desktop client that you had to deploy, and people just weren't allowed to do that. Or even if they were, they couldn't keep it up to date, apply security patches and so on. So for all these reasons, we had to abandon this attempt after about a year and go back and have a think about what we should do instead. And so what we did was we thought about and decided to build our own system from the ground up. By then, clouds had become available, and so we decided to build a cloud-based system. And so we had 3 design rules. So this is work that I did with colleagues Hugo Hayden and Simon Woodman over a number of years. And the 3 design rules that we had would be that it's going to be an integrated solution. We'd noticed that the 3 common things people needed to do were to store data, to share data in a controlled way, and to analyze data. So we were going to try and build a system which offered those 3 in an integrated manner. And then we had this rule, no software deployment by the user. So we didn't want this problem of trying to get end users to deploy clients on their desktop or their laptop. And this was made much easier, as it happens, because HTML5 was coming along. So for the first time, we had ways through, you could build very rich web interfaces so people could just go onto a web browser and do their science. And third, easy to use. So this is something we always put in everything that we try to do. And I'm not sure, it's always very difficult to build easy to use systems. And I'll show you a video in a little while so you can judge whether or not we achieve that. But that was one of our aims behind the design, because we were aiming at people in this long tail, not in experts who could spend a lot of time learning how to use systems, who understood what was going on behind the scenes. We wanted to try and get the ability to do science, do data analytics out to people who had not been able to take advantage of advances in the field before. And so we built a system which is called eScience Central, which is still the basis for almost all of our projects. And it looks something like this if you take the lid off it. So at the bottom, you can deploy it on clouds, or you can deploy it on your own resources. I'll talk a little bit later about why we think it's important to have a common platform you can deploy internally on your own IT or externally on a cloud. And then you can upload data into the system. You can attach metadata to it so that you can search for data with particular characteristics. Also, when you find data, you can interpret it. On the left-hand side, we have a workflow enactment engine, and we have ways so you can package up your services and load them into the cloud for execution. And in the middle, we have ways in which you can describe connections between people and projects. And that's the basis for the security system. So every time you put anything into the system, be it a workflow, a service, or data, then it's private to you, but you can choose to share it with individuals or with projects if you choose to do so. And at the top, as you can see on the top right, these are the scientists who are using a web browser to do everything that they might want to do with this system. But also we provide an API, so that means that you can write a program which actually does everything that you could do as a human by clicking. And I'll come back to why we've discovered that's important later. So here's a little video of it in action. This is my colleague Simon driving this. So what he's going to do is he's going to upload data into eScience Central. So you can see at the back, this is the data pane. So these are all of the files that he's either uploaded or that other people have shared with him. So he's uploaded a new file, which is this one on the bottom left. And what he's going to do now is to have a look at it. So we version everything. So you can see that there's 4 versions of these files. You can always go back to a previous version of workflows, services, and data. Scientists think that's absolutely vital for consistency when they're doing long-running experiments. There he's viewing the data. This is a CSV file. As far as we can tell, most of science goes on with CSV files. And then here's the security. So he's clicking on this tab. It's just accessible to him at the moment, but he can choose to make it available to a colleague, in this case his colleague Hugo, or to a project. So he's uploaded some data, he's made it available to a colleague, and now what he can do is to analyze it. So on the left, you can hopefully see there's a set of workflows, and you can choose an existing workflow and click to run it. But what Simon's going to do here is he's going to create a new workflow. So this is where we're able to take advantage of HTML5. So what happens is on the left, you can see there's a set of categories for services, and in each category you can drag a service out onto this palette in your web browser. If it's a service that has properties you can set, you can do it in this way here. So what Simon's doing now is to select that file that you saw being uploaded, because this is a CSV load service. And then he's going to do some numeric analysis on it. So he drags another block and he connects it together. So in this way, using a web browser, you can create a workflow. And you can then, once you've created it, you can save it and execute it. We'll see that in a second. We provide a basic set of blocks, but every scientific domain has their own sorts of analysis services that are important, and people are always coming up with new ones. So we provide a way for people to take code that they have for a service and to package it and load it up into the system so it appears as one of those services in a category on the left-hand side. And you can do that in Java or .NET languages, or R is becoming very popular, particularly with statisticians who we have now using the system, Octave and a few other languages as well. So here's Simon. I think he's almost finished creating this workflow. This is building a model of some data, and he's using a neural network to try and model it. And so he's finished. So he clicks to save the workflow, and now he can click to execute it. And so this is executed in the cloud. Automatically the system grabs the resources to do that, and it creates at the bottom some new data, which Simon can click on, and then he can view it. So, and there it is. So in the red, if you can see the red, that's the model that's been produced, and the green is the raw data. Okay, so that's the basic features of eScience Central. So let's have a look at using it for the wrist sensor application that we saw earlier, with trying to understand people's activity. So this is what's running in the hospital at the moment. So this is a simple just a Windows application, in fact. And so when the patient arrives back in the hospital with a watch, the nurse takes it off them, plugs it into the computer, types in a patient ID, presses a button, and the data is automatically uploaded into eScience Central, where it's analysed, and then a report is produced for the medic. And so here's one of the workflows which we use to do that analysis. And this is two pieces of the analysis that we produce. So we're still experimenting with the medics as to what's the best format to present them with this information. They quite like the one at the bottom, which is just a simple pie chart. So for the waking hours of the patient, this is what they were doing. So split into different levels of activity. Running at the top, most of the patients we're doing trials on at the moment are over 80 years of age. So we never see much in the running category, but you see quite a lot of light activity walking as well. And at the top, there's a more detailed sort of analysis for the medics, so they can get a view for each day of the patient's activity. So although medics are interested in overall information about a patient's week, like the pie chart, they also have things they want to check. So one thing I've discovered is that medics don't like it if people have lunch and then go to sleep. Apparently that's very bad from the point of view of for people suffering from obesity and diabetes. So on this graph that you can see at the top, there's a timeline at the bottom. This is from midnight to midnight in one day, Wednesday. This is a couple of years ago, this particular timeline. And you can see, you might be able to see red marks at the top, and that's when the patient was sleeping. And you can see one which is just after lunch. So I imagine that the medic talked to the patient about that and tried to encourage them to go for a walk after lunch rather than fall asleep. One of the things that we discovered was that provenance is really important if you're to encourage people to share their data. So it's all very well, there's a big push in science for data sharing, but in general, I think it was Carol Goebel, an earlier Jim Gray Award winner, who said that in her experience it was like trying to get people to share toothbrushes, trying to get them to share data. And what we found is that people would much rather do everything from the beginning again in their own lab or using their own tools rather than trust somebody else's data. But one way to get around that is to keep a provenance trail. So when you give people data, they can click on it and see exactly how it was produced and who did the analysis. And that seems to be a way to dramatically increase the amount of sharing of scientific data. So this is for any data in the system, you can get a provenance report. This is just a part of it, and it shows you, this is for the pie chart, it shows you all the services that were involved in the generation of the pie chart. You can see which versions of those services there were. And if you're really interested in more detail, then we store the data in a graph database, and we can generate these reports, which are these visualizations, which are in a standard OPM, which show you exactly how something was produced. So you've got a pie chart at the top. That's the yellowy orange sun-like circle at the top of that graph. And then the green are the services which were used to generate that data. Okay, I'll give you one last example, because I think this is the way in which we've seen that cloud computing is not just changing the way in which we can do analysis in science, but it's also changing the way in which we can deliver services, healthcare services. So healthcare services are under pressure in most countries. After the banking crash, there's a shortage of money in the economy, and people are trying to make efficiencies. And one of the problems that we find in lots of different areas is that the limitation is in the medics or the therapists who are trying to treat people. So stroke is a real problem worldwide. There's about, as it says, 16 million people a year suffer from a stroke. About 3/4 of those people live, and they need rehabilitation if they're to recover as best as is possible. And the way this is done is that in the UK, and I think this is quite typical, is that after you've had a stroke, you'll be seen by a therapist who will go to your home and have a look at you and work out what the problem is, the extent of the damage, and will then take you through a set of exercises. So they will do the exercises with you, and then they will give you a piece of paper with a list of exercises on and ask you to do that until they come back and see you again, which might be in a week's time. And so the problem is that, well, two problems really. One is that for anybody who's ever had something like a bad back and gone to the gone to a physiotherapist or a doctor and they've done some exercise with you and they've given you a piece of paper to take home with all these exercises you have to do, 10 of these, 20 of these every day and so on, then if you're like me, then after a couple of days, you might do it diligently the first day. By the second day, you're starting to lose your interest because it's very boring. And by the third day, you're only making a token effort at a lot of these exercises. And people who are supposed to do these exercises when they've had a stroke suffer from this same problem of the boredom of doing these exercises. And then the second problem is that the therapists have no idea about whether or not these the patient is doing these exercises, and if they're doing the exercise, are they doing them right? And if they're doing them at all, is it really causing an improvement in them? And so they have to schedule their visits without any knowledge of how the patient's doing. If they had that knowledge, then they could plan their time better. They could go to see those patients more regularly who needed help, and those patients who were doing fine, they could see them less often. And so they could be much more effective in delivering their service. But they have no way to know how to do that. So a group of colleagues, including neuroscientists and people working on games, as well as our cloud researchers, came up with a way to do this, a different way to do this. So this is a trial. You can see a video here with a trial with a patient. And what they're going to do is to play a game. So this is a circus game. So this is a patient who's had a stroke. And what he does is he follows the movements, which you can see from a little avatar in a circle on the right-hand side of the screen. There, you can just see it now. And if he follows these movements, then he causes the larger character on the left to do things like to juggle or to do loop-the-loops, and he wins points. And points are an incredible motivation for people to do things. It's astonishing what people will do for points. And it's much less boring doing this than it is just following a set of exercises from a sheet. And so the patients like this, the therapists like this, because they find that the patients spend more time doing the exercises. And you can use techniques of games. So if they're doing well, then you can move them up to the next level where you might get them to do things that are a little bit harder and so on. So there he is doing some juggling. And so that's great. So we could give this to people, they could take it to their own homes, and when the patients saw them, hopefully, then these patients would have been much more likely to have carried out the exercises. But we wanted to try and go a bit further. So what we do is, even when patients are in their homes, all the data from the game is sent over a home internet connection back to eScience Central, where we run various analytics over it. So we've worked with mathematicians to try and design analytics which match the assessments that the therapists do. So what happens is the therapist will get the patient to do a set of exercises and they will give them a score. So one score is called the CAHI score, which is a measure of upper limb movement. And we've devised ways through workflows using analytics. So this is one of the workflows which can generate an accurate CAHI score based on how the patients are playing the game. And what this means is that now wherever the therapists are, from a phone or a tablet or a laptop, they can go online and they can get a dashboard which gives them, for all of their patients, information, and they can click on a patient. So the dashboard's at the top, and this therapist has clicked on one of those patients, and at the bottom what they're seeing there is it's a graph showing the change in the CAHI score day on day for this particular patient. So they can see, for example, that the CAHI score increased from day 1 to day 2, and then the patient didn't play the game at all for 3 days, and then played it again with a marginal increase, didn't play it for a day, and so on. So this allows the therapist to decide how best to spend their time. So they'd probably be worried by the gap of 3 days when the patient wasn't playing the game, and they might decide to go out and talk to them about it, which might result in them switching the game or setting the game to an easier level and so on. And they might start to get worried even if the patient was playing the game, their progress, as measured by the CAHI score, wasn't what should be expected. So this means the therapists have much more flexibility in how they spend their time, and they can put their efforts where they think it's going to matter the most. The other thing that we can do is, as we build up, so we're in trials with this at the moment, as we build up more and more information, you can do cross-population analysis. So this is a graph about one particular game, and this tells you something about the popularity of this game across the whole cohort of patients. So this says that on day on week 1, then patients in general played this game somewhere between 3 and 4 times during that week, and then it tails off a bit, and then it dives down in week 4. So this might tell you, you might compare this with another game, and it might show actually this game is pretty good at getting people interested, or it's not as good as another game. But you can also do things like, a judgment here might be that after day 3, people get bored with this game. Sorry, after week 3, they get bored with it, and so it's probably then worth going and switching to a different game for them to keep up their interest. So we collect all of this information. There's all sorts of different things you can do to measure the effectiveness of the different games, to see how a patient who comes in with a particular starting point, a particular level of problems from the stroke, to see which is the best particular game to give them, and to know what the expectation is and how they should improve over time. One thing that's happening in the health service in the UK, which may be driven by things like this, is that payment by results is becoming important. So you get third-party providers who can provide treatments for particular conditions, let's say stroke, and you don't pay them up front, you pay them by results. And so one of the things that people are thinking about is, if you've got this sort of information, you could actually measure the level of the patient when they arrived, measure how they were improving over time, and when they got to a certain level that was governed by the contract with a third-party provider, then that could automatically trigger a payment. So that would be a real change in the way that healthcare services were delivered in the UK, but it could be enabled by this ability to capture detailed information, not just about individual patients, but across a whole population of patients. Let's imagine that the trials go well. They seem to be going so at the moment, and we want to scale this out to perhaps hundreds of thousands or even millions of stroke patients in the UK around the world. Then would we be able to scale? So we put a lot of effort into scalability. I said earlier, this is one of the problems of cloud. Clouds give you lots of nodes, but it's up to you to spread out your work across them and scale it up as you get more data, as you need to do more analysis. So this is how we do it. I won't go into a detail, but what happens is that every time there's a workflow needs to be executed, it goes in a queue, and you've got a set of workflow engines which you can run on a set of cloud nodes. So you can have as many of those as you need, and what happens is when they're running out of work to do, they can go and grab some more work from a queue and do it and return the results back into the system. And so that seems like quite a simple architecture, and it looks on paper like a lot of architecture diagrams as if it will work well and be very scalable. In fact, we found it took us about 2 years to tune the system so that we get these sorts of results with it. So this is typical. So this is a particular experiment that we've done running on 200 nodes, as it happens in the Microsoft cloud, and we're getting about 90% efficiency for scalability. It took us about 2 years to get up to 90% efficiency, working closely with people in the Azure team, in fact, at Microsoft. But the attraction of having this cloud platform is that now all of the projects that we run across our platform benefit from the work that we did. We removed a lot of bottlenecks in order to make this scalable. And so all of those projects now benefit from that. Whereas if you're back to the building individual applications for individual projects, then the danger is that any optimizations that you do will only benefit that one particular project. So I think this is another reason for why it's a good idea to actually have a platform, which means that all the effort that you put in through your projects to add new features, to improve its capabilities, every project benefits from that, and not just the one you're currently working on. So I hope I've shown you some things about some of the work that we've been doing on clouds. I'll come back to in a minute about some conclusions that we've drawn from doing this. But I wanted to just segue into thinking about why I do this and why I think it's good for computer scientists like myself to work on eScience applications. And for this, I need to go back in time. So Harold mentioned some work I'd done in industry. So this is going back 20 years. This is a machine called the ICL Gold Rush Mega Server, which sounds like a 1990s name for a computer. I guess marketing people would think of better ones now. And this was a project that I worked on. I started working on this when I was doing my PhD at Manchester University. I had a collaboration with a local company, ICL, and we started with, as you do, with some, at that time, some sketches on blackboards, and eventually we built a little prototype, and it got to the point where ICL decided that they wanted to turn this into a product. And so they asked me would I move across, and so after 5 years into this collaboration, I moved to work for ICL, which I worked for about another 5 years, and after about 10 years of this endeavor, we produced a product which we then released and sold around the world. And it was a parallel database machine. So at the time, ICL was a mainframe company, and their mainframes, it was quite expensive doing high throughput transactions on a mainframe, and so they wanted something faster. And so we built this parallel database machine, which had all sorts of exciting features at the time. So it had 64 nodes in those cabinets, each of which ran 2 Spark chips. And I can remember that the excitement that we had when we got our first delivery of 1/4 gigabyte disks that we could put into this machine to really mean that we could store enormous databases and process them. And so I worked on this for many years. The first one that we sold was to Johannesburg City Council, and apartheid had just fallen, and they had a small computer that they had their electoral register on, and suddenly, because of the fall of apartheid, they had many millions more people on their electoral register, and so they needed a bigger machine, and so the first one that we built went to Johannesburg. And after about 5 years at ICL had invested about $50 million in this over the time. We had about 150 people working on it, and I was ready to move on and design the next generation of it, because I don't know whether anybody's worked in industry, but often what happens, you release a product and then you're excited because customers use it, and then customers go and ruin everything by finding bugs and wanting support and wanting extra features, and so that's where your attention then turns. And I found that was a much less interesting part of working in the computer industry than actually designing new systems. So ICL weren't interested in immediately ploughing on and putting a lot of money into in the next generation. So I went back to academia and I moved to Newcastle. And I can remember on my first day at Newcastle, I was led into a small office, and so I'd left this company with this $50 million project, 150 people worked with me. I was on my own in this office. I can remember thinking, what on earth do I do now? That was my very first thought. And then my second thought was, why on earth did I do this? And for a while, things were it was quite difficult, because you realize that you don't have the resources in order to do the sort of thing that you could do at scale in industry. But I started, so we tried to do some bits of work here and there, and we built some models, and we got a little bit of money to build prototypes. But really, I realized that the two things that I was lacking weren't particularly resources in general. It was two things. So one was a source of problems. So at ICL, there was always people banging on your door coming in from banks and building societies and local councils saying, why can't your machine do this more quickly, or why can't it do that or the other? And in university, then I'd lost those stream of people coming to me with these problems, which I realized were motivating the research that I was doing. And the other thing I'd lost was access to data. So in ICL, we had all of these banks and councils who would give us examples of the data that they wanted to process through our machines, and we could use those for valuation. We could see how fast we could run all of these different sorts of database workloads through the system. And it was very hard. I couldn't get data, and I can remember ending up writing programs to generate dummy data to process. And it was all a bit demoralizing, actually, and after 5 years, things weren't going so good. And I went and I remember I gave a talk at Essex University, and there was a professor there who I knew very well, and I gave my talk, and we went to the pub afterwards, and I was explaining these problems to him, and what he said was that, well, you need to get used to what you have to do in academia, which is to work on, and he said, toy solutions to toy problems, and I can always remember that. And so his idea was I needed to set my sights lower, start working with smaller amounts of data, and working on problems that I'd generated myself rather than the real problems from the outside world. And I was rescued from this by something that happened in 2001. and that was the UK Science Programme. So in 2001, the UK government decided to invest a lot of money in eScience, and it was conceived and led and directed by this fresh-faced young man here, who was then a professor at Southampton University, who moved over to take the lead in the project, Tony Hay. And I'm delighted Tony's here today in the audience. And Tony's vision was that it would be possible to transform science by the use of advanced digital technologies. And the way in which he achieved this was through social engineering, so trying to get computer scientists like me to work with scientists across a wide range of different subjects. And for the first time in 5 years, suddenly I had lots of really interesting problems, and the problems were much more interesting even than the ones I'd had working in industry, because it was more exciting to work with, say, neuroscientists trying to understand how the brain worked than it was to work with a bank trying to run a set of customer transactions through slightly more quickly through their machines. And we were drowning in data, so every area of science suddenly was generating data. So biology was probably one of the first ones, but there's also astronomy. Also had huge amounts of data which were available. You could grab it and you could work with scientists to extract lots of interesting things from it, and hopefully drive on the science as well as providing interesting challenges to a computer scientist like me. So this program, which Tony conceived, was copied widely across many other countries, and then Tony continued it when he moved to Microsoft. And so I think for me this was the real saving of my career, this opening up of this new world, that it was possible to work with scientists who had interesting things to do and lots of data that we could work with them on. And it was through Tony that I met Jim Gray, actually. So Harold mentioned Jim, and I'd known Jim because by reputation, because working on parallel database machines, Jim was considered to be the main person in the database field at the time. And that was because, very unusually, what he did was he matched the practical, so he really designed and built through his career database systems which were faster and better than previous ones that had been available. But he also could do the theory side as well. So he had equal respect, which is very unusual for academics, but also from people in industry. And I got to know Jim through Tony. So I remember we went to his house once for breakfast, and I remember sitting in his house was in San Francisco, looked out over the harbour, and I can remember that he didn't know how to make tea. So Tony had warned him that, although Tony drank coffee, that I drank tea on a morning. And so Jim had phoned his wife up. She was out of town with her friends and family, and I can remember that he was standing with a kettle with boiling water in and a cup, and he had a tea bag and a set of detailed instructions and a stopwatch, which he then used, like carrying out a chemistry experiment, to make me a cup of tea for breakfast. And after that, he would do things that really surprised me. So he would send me long emails giving advice and guidance on what he thought I should be doing, or giving feedback on some of the papers I'd written. And I can remember once, for example, that I was given a talk, a keynote at a conference, and it was some work that I'd put more effort into, that I'd really put my heart into than anything else over the previous year. And so I wrote the paper, spent a long time writing it, and then I gave the keynote. And while I was giving the keynote, you could see it just went down like a lead balloon. You could see the tumbleweed rolling along in front of the stage as I talked about these new ideas. And I was quite demoralized by this. And then about a month later, I got an email from Jim saying he'd read the paper, he really liked it, and he was sending it around to his friends. And so that was a huge boost. And the amazing thing about Jim, I feel, is that although he was the top man in his field, a very busy person, had lots of demands on his time. He was always, people were always wanting him to go and give keynotes, for example. But then he would spend time sending long emails to people like me, who are nowhere near in the same league as Jim was, to give us advice and guidance in the field. And I think there are very few people who are at the top of their game in any discipline who are actually put that effort into bringing on the next generation, as well as keeping their own career going. So that's one of the reasons why it's a really a great honour to get this award in Jim's name. So just to end with a few conclusions. So I'm I'm always reluctant to make very sweeping statements, but I do think this one is true. I do think that cloud computing is going to revolutionize eScience. And I think that hopefully through some of the examples that I've shown, you can see the benefits of this. The agility, the ability to just go and grab resources as and when you need them. Not have to put in big grant applications that take you two months to write in order to try and get the compute resources that you need to try something. The fact you can just go and grab the resources to do it immediately. The democratization of it, the fact that you don't need to be in a center with lots of resources in order to be able to try out your ideas at scale. The ability to share. So clouds they're not the only way to share data, and they don't guarantee you'll share data, but it's much more likely, I think, that people are going to build systems which allow data sharing and sharing of computations if they're in a cloud where naturally you can share them among other people, rather than, say, if they're on your laptop or the local server in your university. And I think we're starting to see that. The guys who we work with in the medical school at Newcastle, Mike Chanel's group, who do the movement analysis work, their aim is that this should be a common repository which they can make available, so anybody can go and get the data, add their own services into the system, and try them out and make them available to others. And the cloud naturally lends itself to that sort of approach. And finally, impact. So talking about the second example with the stroke rehabilitation, the fact that if suddenly we do decide, or we get the opportunity to roll this out to hundreds of thousands of people, we don't have that thing that used to happen in universities where you had a little prototype that was running on a small server in your lab, and it was good enough to get a couple of papers out of it. But then if you wanted to do something at scale, then you needed to start again and build a scalable system on an entirely different sort of architecture. I think what clouds do is going to make it much more likely that people are able to take something which they've done through their research and then to scale it out, to get it out there to benefit society and a wider group of scientists. But having said that, then there's all of these barriers. So I've mentioned quite a few of them. How do you build scalable systems? It's the issue of dealing with security, problems of building systems that don't fall over at inconvenient times, and also auditability, building systems so you capture what's being done so you can get reproducibility, something else that's important in science. And so I think the thing that we've learned is that cloud platforms, we do think, are the way forward. So rather than solve each problem individually and build out a siloed application stack for that, I would encourage people to think about whether you can generalize what you're doing and build some common services which you can then apply across a wide set of projects. And I've talked about one of those, eScience Central, which is ours. It's open source. You can download it from SourceForge if you want to try it, or you can go, if you go on the web, there's also a version that's up there where you can just register through the web and log in and try it out. But I'm not claiming it's the be-all and end-all. And what I'd like to encourage other people to do is to think about other sorts of platforms, ones that might, in the end, be better than the ones that we've produced. But I do think that this approach of platforms really is the best way forward. And finally, to come back to what I said earlier, that I really think that eScience is really important for computer science. It generates all of these exciting, interesting challenges that computer science can use to come up with new research ideas and to test what they've done. My hope for the coming years is really that this vision of eScience, which Jim Gray and Tony Hay have been propagating over the last couple of decades now, that will really continue, and that new young computer science will take up the challenge and realize how it's a really good way to find interesting problems to work on, which can have real benefits to advance knowledge and also help society. Thank you. Okay, I'm going to chair myself to answer any questions. So any questions anybody has? Darren. Yes. Yes. Yeah. So we're at the stage where we can do trials, but we're not able to do it at scale at the moment across a wide set of patients. So the way it works in the UK is you can apply for ethical permission to do trials on a small group of people, but there would be a set of hoops you would have to go through if you were to really roll it out as a production service in the health service. And it's forced us, even in these trials, to address some issues, but there are others that we leave for the future. So one of the issues that's really important, of course, is security. And I didn't have a chance to really to talk about this in detail, but one of the reasons we found an advantage in having eScience Central as something that's portable is that what we can do is we can run it on a public cloud like Azure or Amazon or OpenShift for those sorts of analyses where there's no issues to do with privacy or security. For cases where there are, then we can run it on our own internal IT. Now, the trick, and this is where our current research is for it not to be an either-or decision. So it's quite one of the barriers to clouds is you get people who say, well, there's some sensitive data in an application, therefore we can't take it out to a public cloud, we'll have to run it internally. And what we've been doing is we've worked on tools so you can describe your application, the security levels that you require within that application for sensitive data like patient data, and you can press a button, and what it does is generates a workflow that spans both the private cloud and the public cloud, where we run eScience Central on both. And so then that means that the secure data remains on the private cloud, and the data that's anonymized, but the data where you really need the scalability of the public cloud can go out to there. So that's been our main drive. The bit we haven't done yet is if you wanted to, say, go through all the regulations that you would be required to get it out there, say, in the US, then really that is a whole new set of regulations that we'd have to go through, and that would require extra resources to do that. So we're just at the stage where we've got an idea of what would be required if we got to that stage, but we haven't done that yet. Dan? Yeah, so that's a good question. So the idea is, are we going for throughput, or are we trying to reduce the response time for a big workflow which might have internal parallelism? Well, we can do both. So in the main, what we find is that although MapReduce is the big hammer that people are hitting every nail with, almost everything we do is map. So, and there's very little reduce ever involved. So you get lots of data in, say, sensor data from lots of patients, and you need to analyze it, and they're all independent. So we do lots of maps, and that makes it easy to spread it out across a set of nodes. In fact, the graph that I didn't have time to go into it, but the graph that I gave showing that 90% efficiency, that was for one workflow. And that was a workflow that we used to do some chemical informatics with some cancer research scientists to try and predict the behavior of molecules. And it starts off, and then there's points where you can parallelize it because you get individual data sets that you can explore in parallel, and you bring it all back together at the end. So although I think it said it had 500,000 workflows, they were actually sub-workflows that were spawned off from the top-level workflow. So the way in which it works is that you start your top-level workflow, that can then create other workflows which then go into the queue, and then those are scheduled, and then eventually you can combine them all back together again. So we've got a bit of experience of both, and in that case we got good efficiency for the case of reducing response time. But as I say, in the main, what we find is most people in science want to do map. Thank you. Yeah, okay. Yeah, sure. So the idea was that the project I've talked about has a focus on social exclusion, and I talked about some of the perhaps the more medical end of the projects that we do within that. But what about other things? And the two examples that the gentleman gave. So one was about traffic congestion and pollution, and the other one was about violence. If we take the two separately, although they can both combine into one at times, I guess. But if we take the traffic one, then we've done quite a lot of work on analysing traffic flows and pollution in Newcastle. So using very small, cheap sensors which are spread around the city, and combining that with the information that you can collect from traffic sensors, which are usually loops, wires that are under the roads. And as a result of that, then you can start to build models, and you can start to see what causes particular problems in the hope you can head it off. The one thing that's interesting is that there's always two ways in which you can use data analytics. So the first thing is to understand, which is what we can do in that case. But the second thing is then to try, what can you do about that? And that's why in our projects we have experts in particular domains like sociologists, traffic experts, and so on, because what you need to understand is how policymakers could be influenced in order to change what they do. So how can you get politicians to change the way in which the road systems work, perhaps in 5 years' time to have a much more dynamic system of routing people around cities, perhaps using incentives. So we have congestion charging in some cities in the UK. Could you have differential congestion charging if people would be prepared to go a slightly longer route, but which would reduce the levels of pollution? And so, and I wouldn't underestimate the difficulties of doing that, trying to understand the levers by which policy changes and trying to cause those to have an effect. And they seem to be different in different domains as well. So that's why we try to hook up with experts in those areas. And we do quite a lot of public engagement, so we get people in from those, from the government and the councils and so on, who could potentially have an impact on that, and make them aware of what we're doing in the hope that they will then take it into account. In the other area of violence, then that's a more difficult area. We've done, aside from this in the same project, we've done some work on social media analysis, which the police are very interested in. So trying to understand before things happen, what information you might get which might lead you to predict that something's going to happen in a particular place, but also afterwards then analysing what happened in order that then you could in the future look out for those particular patterns that you've detected. That's at a very early stage, and it's very difficult. I mean, one of the problems you've got is a real lack of information, because there's only a certain proportion of the population provide information on social media, and it's not always accurate. And one of the things that used to happen was that which was very helpful for that, was that almost all clients for social media automatically geotagged all of the information. And we had some riots in the UK, I think it was 2 years ago, 3 years ago, and they were the first riots that we'd had in the era of Twitter. And some people were tweeting things like, I'm going now to set alight to this building, and in the tweet they would be geotagged, and so the police could just drive along and pick them up when that happened. But now people seem to have become more savvy to that, and also a lot of the people who provide clients for social media, the default setting is now off rather than on for geotagging.
Hi. You mentioned that your team spent about 4 years achieving the 90% scalability of your system.
Yeah, it's about 2 years worth of effort with some...
2 years?
2 years, yes, with some experts in the Azure. We started off at about 40% and got up to 90% in 2 years.
Could you mention one or two of the problems that you faced during that time and how you fixed it?
Yeah, okay. So there's really two things that we needed to do. So one was the scheduler. So the scheduler wasn't feeding the workflow engines at the right rate. So, I mean, I've worked on parallel machines for about 25 years, and it's always the same problem. So you know the problem that if you have a central queue with all your work in, then when a workflow engine runs out of work to do, it takes a while before it can get the next piece of work from the queue and set it up to run. So then what you do is you go and try to preload your workflow engine with tasks to do, so that they're sitting ready and waiting. But then if you do that too much, then what happens if the central queue runs out and there's no work on some other workflow nodes? So getting the balance right there was one of the things that we played with. The other thing was it's quite complex to run a workflow in a scalable way, because what you have to do is it's no good just so we can run a workflow engine on each node, but and you can send the description of the workflow which says run this service and then send the data to this service and run it. But for scalability, what you have to do is to dynamically deploy those services on that node with the workflow engine. It's no good having a service deployed in one place and sending everything to it. So what you have to do is to have efficient ways to package up services and efficient ways to then dynamically deploy them as and when required. And that's an area that we're still working on. We think that developments like Docker, for example, are going to be a real help in that area. But that was the second point in our system that was a bottleneck. Another one? Okay, so the question is about data movement. So at the moment, we take a relatively straightforward view. So what happens is that when we run a workflow, it's all run on the same node. So we fetch the input files, and then any intermediate files remain on that node as they move from one service to another. And we have optimizations where we can stream them through the nodes in order to, for example, to try and make best use of main memory. Where we started to do some work is on what I was saying earlier, on Darren's question, where we got multiple eScience centrals running on different clouds. And the way I described it, we described the application, and we have a tool which, if you describe the security requirements, it works out how to divide it up across these nodes. Now, what invariably happens is you get multiple options, even for a very simple workflow. And the question is, which one do you choose? So then we have a system where you can use cost models. And you can do it on pricing, which actually takes into account data movement as well, indirectly, because of course it costs you to move data into a cloud. But you can also, in your cost model, you can have a policy to reduce the amount of data that was transferred between nodes, even though it might cost you a little bit more in price or whatever. So you're trading off, well, we never trade off security, but you can trade off price against performance if you want to do that. Yeah. So at the moment, almost all of our optimizations have been on an eScience settle running in a single cloud, and so we haven't worried about that. But we've started in these cost models to try and use estimates of how long it takes to move data. And one of the motivations for that is that although I described patients going into a clinic with a watch, and then there's a small number of gigabytes of data gets uploaded. Occasionally we are involved in remote studies, and then through the post will come 10 terabytes of data on a big disk, which we then have to process. And that really is good motivation for minimizing the amount of data movement. So it's in those cases that we've started to do it. But we have a vehicle for doing it, which is this cost model mechanism in our tool, but I wouldn't say we've done a lot of work in that area, and we'd be keen on anybody who wanted to work with us on that.
Oh, but I can't speak loud. Okay, yeah, I know. Okay, so I'm sorry. You were talking about scalability, and I was just wondering about domain expert scalability. So you start up working with a group of experts from other domains,
Yeah.
and all of a sudden you realize that you missed a facet of that problem, and in order to finish your work, you'd have to bring in other people. And then it may scale up to, whatever. So is there any kind of advice or expertise that we need to handle this expert scalability?
Yeah. So that's a really good question. What we find is that if you look at what we embed in the cloud through eScience Central, then we end up with these workflows that when data arrives, you use the workflow to do some analytics. And what we find is that most of the people we work with are perfectly capable of loading some data and clicking on a workflow to analyze that data and produce a result in a form that they understand. And that's why we put effort into allowing sharing of workflows by individuals and within projects. Because what you find is that then there's a next level, there's somebody who can actually create the workflow. They're a level of expertise above that, and they do that, and they've got the authority because they're the project lead or they're running the lab to say to everybody, look, whenever we get this sort of data, use this workflow because I've blessed it. The next level of expertise is people who can actually write the services that are part of the workflow. And what we find is that so this is probably going up by factors of 10. You know, so for every person who can write a service, there's 10 people who can combine service into workflows, and then there's 10 people who can use these workflows in order to do their analytics. So the thing that we found is to not treat all scientists, all users the same, and to try to work out where they fit in this pyramid and to make best use of their talents in there. So for example, if somebody can write a service, helping them to package it up and putting it into the system so that others can use it. People can write workflows, then making sure that other people in the project are aware of this workflow which they can use, rather than have them try to build a workflow from the ground up themselves. So that's the approach that we found is most effective. Okay. Thank you, Paul. Thanks.
So thank you, Paul, for an illuminating talk and for setting the tone for the rest of the things we'll see over the week. It was very well done. Thank you very much. Now we're going to have a coffee break in the next room, and I don't know if the next room means that way or this way. She's pointing over there. And remember, when you come to the next session, if you're coming to the one related to our workshop, it's upstairs. And we'll see you there. And see you at coffee too. Thank you.